Optics by Olivia Bainey, Jamie Lee, and Swathi Menon. You use your camera to take a picture and you stand in front of a mirror to fix your hair. These are just a few examples of the applications of optics. But what is optics? Optics is a study of light and its behaviors. However, based on various aspects, optics can be split into two specific branches of study: physical optics and geometric optics. Physical optics is more oriented towards the study of the effects of light waves. This includes topics such as diffraction, interference, and polarization. Geometric optics, on the other hand, focuses more on the properties of light rays when it strikes a new medium such as lenses and mirrors. In this video, we will be explaining the concept of geometric optics by defining key terms and presenting important mathematical equations. We will also provide an example of how geometric optics can be used to collect solar energy.
There are two main types of mirrors and lenses, concave and convex. When you're looking at a concave lens or mirror, it's like you're looking into a cave. When you're looking at a convex lens, the round part is facing towards you. A ray diagram is a diagram that shows how light rays from the object reflect off of the mirror and creates the image that you see. The first step in making a ray diagram is to draw and label the focus. The focus is a point that is half of the radius away from the edge if the mirror or lens were to be a complete circle. For a convex mirror, the focal point is to the right of the mirror. To make a ray diagram, first you draw your object, in this case an arrow, on the left of the mirror, so it is on the same side as you are. Next, you pick a point, in this case the top of the arrow, and draw a line that is parallel to the ground from that point to the mirror. After that, you use a ruler to connect the point you chose to the focus, and then draw that line from the point to the mirror. To symbolize the reflection from the mirror, you then do the opposite of what you just did. For the line that was going towards the focus, draw a parallel line to the ground at the height of the mirror at that point. Similarly, for the line that was originally parallel to the ground, connect the edge of the mirror there to the focus with a ruler, and draw a line from the mirror at that point back to the left. With the convex mirror, you see that the two resulting rays depicted in blue diverge. Therefore, you need to extend them back in order to find out where the image is. To do this, you just extend the blue lines to the right, and where they intersect is the point on the image that corresponds with the point that you chose of the object. Then you can use that point to draw in the rest of the image. With the convex mirror, you see that it creates a virtual image that is smaller than the object. To draw a ray diagram for a concave mirror, you follow similar steps to the ones that you did to draw a ray diagram for a convex mirror. First, you do draw the focus, which for a concave mirror is to the left of the mirror. Next, you also draw the center, which is the same as 2 times the focus. After that, you draw your object, in this case, once again, an arrow. And you still pick a point on that object, that in this case we are still using the top of the arrow. You then draw a line that is parallel to the ground from the point to the mirror. After that, you draw a line from the same point through the focus this time, that is on the left, to the mirror. To then draw the reflected light rays, you connect for the line that went through the focus initially, you take a parallel line to the ground and draw it back to the left from that same point on the mirror. For the line that was initially parallel, you connect the point on the mirror to the focus with the ruler and draw a line to the left. Where the two reflected rays intersect is the point that corresponds with the same point that you chose originally on the object, and therefore you can draw in your image. When your object is to the left of the center, your image shows up reflected between the center and the focus point at a smaller height or size than the initial object. When drawing ray diagrams for concave mirrors, you can see that the image does not always end up in the same relative location or with the same relative size as it does with a convex mirror. To solve this, you can just remember the general places where they're located, or you can draw a ray diagram each time. When the object is located on top of the center, or 2F, then the reflected image is at the same location except for upside down, and it retains the same height. When the object is located between the center and the focus, the reflected image is to the left of the center, and it is larger than the original object and upside down. When the object is on top of the focus, there is no reflected image, as the rays are parallel coming back and they never intersect. When the object is in front of the focus, you can see that the reflected image is actually a virtual image, and it is larger than the original object. It is also located to the right of the mirror in a ray diagram. This is a summary of the locations of the images depending on the location of the object originally in relation to the center and the focus for a concave mirror.
The lens equation, or mirror formula, expresses the relationship between an object's distance from a mirror, the image's distance from a mirror, and the focal distance. To start, we have a concave mirror and a principal axis, labeled as the focus and the center of curvature, or 2f. And this is the lens equation. For a concave mirror, an object behind the center of curvature will produce an image between the center of curvature and the focus. Now the lens equation is 1 over dO plus 1 over dI, which equals 1 over f. dO is equal to the distance of the object to the mirror, dI is the distance of the image to the mirror, and f is the focal distance, or the distance of the focus to the mirror. The magnification equation relates the ratio of image distance and object distance to image height and object height, or the object's magnification. Again, we have a concave mirror and a principal axis. Labeled is the focus and the center of curvature, or 2f. And this is the magnification equation. Once again, for a concave mirror, an object behind the center of curvature produces an image between the center of curvature and the focus. Now the mirror equation states that the magnification of the image is equal to negative dI over dO, where once again dO is the distance of the object to the mirror, dI is the distance of the image to the mirror, and f is the focal distance, or the distance of the focus to the mirror. There are a few important sign conventions it's important to make note of that apply to both the lens equation and the magnification equation. To start, f is positive for concave mirrors and f is negative for convex mirrors. dI is positive for real images that are on the same side of the mirror as the object, and dI is negative for virtual images that are located behind the mirror.
Geometric optics has many applications. However, we will focus on how geometric optics is used to concentrate solar power. We will be presenting to you 3 different ways that solar power can be concentrated: the parabolic trough system, power tower system, and parabolic dish system. The parabolic trough system operates by concentrating the sun's energy along several receiver pipes found throughout the design. This system concentrates the sun's rays through the use of reflectors made out of metal mirrors. The power tower system is a solar collector that uses movable mirrors called heliostats to focus the sunlight. As you can see in the drawing, the sun's reflected rays are aimed towards the top of a collector tower where the solar energy is converted. And lastly, the parabolic dish system. The parabolic dish system consists of a parabolic dish surface upon which mirrors are distributed. The mirrors are oriented in a way that the sunlight reflections will concentrate on the receiver or engine, as you can see in the drawing. All of these solar collecting systems share a similarity in that they use mirrors to concentrate the solar power. However, the type of mirror used varies for each system. While power tower systems use flat or plane mirrors, both the parabolic trough system and the parabolic dish system use concave mirrors. Carefully designing the orientation of these mirrors in each system allows the sunlight to be reflected towards a collector that generates electricity. By using mirrors as the new medium upon which the light rays come into contact, geometric optics is applicable in the concentration of solar power.